Okay, so let's get started. We are going to continue discussing health issues, in particular the deworming project, today and next lecture, maybe even a little bit into the following lecture. Problem set 1 is due on Tuesday. A number of you have sent questions or clarifications. I think most people know what's going on. On Tuesday, please bring a paper copy, a hard copy of your answers, because there's answers to the questions, plus a paper copy of your programming file, the do file in Stata, and your output file, the log file. We'd like to see all that just to see where your results are coming from. Do file and log file. Yeah, I guess, actually, now that I think about it, the do file is sort of in the log file, so maybe just the log file would be okay too. The log file has both, the results and, yeah, good. Okay, we're going to start with a quicker question right away just because I want to get feedback, and this is the easiest way to get feedback, which is these lectures are being posted on the ETS website with a 2-week lag. And I checked today, lectures 1, 2, and 3 are up. There's a problem with the audio in lecture 2, but I think from what I checked and from what they told me, lectures 1 and 3 are okay. So I just want you guys to answer this. So let me start the poll, just to find out if people are like avidly watching them, sort of watching them, or if it's like kind of a waste. But I'm just trying to figure out if we're going to do this again in the future and sort of how much people are accessing it so far. Yeah. Are there 6 up? Oh, is that right? Okay, I only found a few. So have people found 6 lectures? Oh, as of today. Okay. Okay, I only found 3, which would make sense because there's sort of a 2-week lag, so only really through lecture like 3 or 4 should be up. That's all I found, but maybe they put some up today, or you saw 6 up? Oh, okay. So make answer A all 6 lectures, and B is 2, 1, the rest the same, let's say. I don't know. No, forget it. A is 3 or more. So put in a new answer if you want to. 3 or more, 2, 1, 0. No thanks is E. Okay, let's just go another 10 seconds on that. I think most people are in. Oh, you're not kidding. Good stuff. Got it. Okay, so are people watching? So most people haven't watched, but a fair amount have watched at least some. This is pretty interesting. If I were an undergrad like you guys, I would have been in eCamp. I would have been like taking my notes in class. Of course, there was no internet. Or like it existed, but it was this mysterious thing. Okay, this is good to know though that 80% either are watching or plan to watch. So it seems like there is some value to lectures being online. Thank you. Great. Any questions before I get started on the content of the lecture? Yeah. I put the delay on purpose because I want people to come to class, and I'm afraid if like the lectures are like there day of right away, it gives people less incentive to come to class, and so much of the back and forth and the discussion and the participation is a big part of the learning. Before the midterm, I'll fast forward them so they'll all be online, and before the final as well. So we've set it up with them so everything will be available when you're studying for the exams. But, yeah, so 2 weeks later you can do that. That's the way it's set up. I'm still figuring this out. It's the first time I'm doing it, but my fear really is people wouldn't come to class if like day of they could just get the lecture. So that was the idea. Yeah. Okay. No, this is really useful. I'm still, like I said, I'm still trying to figure this out. Should be like a day lag, a week lag, a 2-week lag. So this is good feedback if people think that. So thank you. Any other comments or thoughts? All right, let's get started. So just to take 2 minutes and recap where we were last time, and then we'll just keep going with the estimation of treatment effects in the case of an experimental setting, a randomized experiment like the deworming project. The way the setup of the project worked was there was this list randomization where the 75 schools were divided arbitrarily into 3 groups, group 1, group 2, group 3, each with 25 schools. The first group of schools, group 1, started receiving the deworming treatment in 1998, and they continued receiving it in 1999. Group 2 started receiving deworming in 1999. So Group 3 were control schools or comparison schools throughout. Group 1 was treatment throughout, but Group 2 switched status sort of in the middle of these 2 years. And the 2004 paper uses data for these 2 years. So we're going through this. This is the basic research design. And I think just at the end of class last time, we were getting into the map of all these schools. The 2 schools were located in 2 divisions, geographic divisions, called Budalangi and Funyula, and really scattered throughout these 2 divisions. And as I mentioned last time, the schools that were excluded from the sample up front were the better off town schools. So in a couple of the towns, there were some wealthier schools, and also the most remote schools, like some of the schools on islands in Lake Victoria were also excluded. But really the bulk of rural primary schools in this area were included in the sample. So 75 out of the 89 schools. And what we went through last time was what an estimation equation would look like if we wanted to get unbiased estimates of the treatment effect of this program, where we would regress the outcome y, like an educational outcome or a health outcome, on the treatment indicator t. But we've assumed that the correct specification looks like the following: that there's some other factor or factors, more broadly x, that could also affect the schooling outcome. And if we don't have very good data on x, we might have an omitted variable bias problem or confounding problem. And the experimental design, the randomized design, helps us get around that by weakening the correlation, or eliminating the correlation, hopefully, in expectation between treatment and x. So again, this is just review from last time. Going through the algebra, what we come up with is if we take the difference between the treated and the untreated, so here the deworming treated and untreated, that difference is equal to the true effect we're after, b, the effect of treatment on your outcomes, plus the second term, which we could think of as the omitted variable bias term or selection bias term. And the selection bias term is driven by a correlation between this variable x and your treatment status. If x has the expected value of x, or on average, this characteristic x, like poverty, we talked about last time, or access to schooling, is balanced between treatment and control, this term goes to 0. And what the experimental design does for us, and I just bolded point 3, again, this is just going through what we discussed at the end of class last time, is in expectation gives us a situation, due to the experimental design, due to the randomization, where on average, that variable x, or the expectation of that variable x, is the same between the treatment group t equals 1 and the control group. And that's the real value of the randomization. Now here we modeled it as if there's one omitted variable x, but in reality there could be a whole wide range of variables, some of which we have data on, some of which we don't. But in expectation, all of those characteristics are balanced between the treatment and the control groups, because there's no systematic reason why one receives treatment or not when it's determined randomly. And that's the real value of this kind of design. So this is what we got up to last time. Let me pause for a second if there's any questions just on what we had gone through. This is the same logic as you would have behind a medical trial. The treatment group and a control group, where the only difference between the 2 groups is the outcome of a coin flip, say. Yeah? Say that again, can you speak up? You mean number 2, d equals 0. D equals 0 is sort of a weird case. It's a case where, for whatever reason, there are no other omitted variables. There's no other characteristic that affects the outcome. But when we're thinking of something like your health, your nutrition, your educational outcomes, your income, we know that there's many factors that affect those outcomes. So it seems implausible to say that nothing else affects them. So it's like almost like a degenerate case. It's not a case that we think holds in the real world very often, and that's why we need these experimental designs. Yeah? So the question was raised about sample size. Is there a minimum sample size you need? Does anybody have any thoughts about that? What are the? There's a couple of considerations here in terms of sample size. Yeah. You said you could use a pilot? Explain what you mean. Okay, so the point is raised that maybe with pilot data you can get a sense maybe of what the data looks like. In general, larger sample sizes have. Okay, so there's sort of 2 advantages. I want maybe the other folks in class to bring them up. Yeah. Okay, so okay, I think you're talking about power calculations. So the basic point about sample in any real-world study or any application is more data is better, more sample is better. And it's better in part because we get more precise estimated effects when we have a larger sample. And by precise, what do we mean? We basically mean that standard errors are smaller. We like small standard errors in our regressions because it means the confidence interval is shrinking. We have a tighter and tighter sense of where the true effect lies. So that's great. That's what we want. Now, the usual trade-off we face in the field when we're designing a project is we only have a limited budget. We can't get infinite sample. So one typically tries to get as large a sample as you can given the budget of your study. And the calculation that was alluded to here is one where you can say, look, let's say I have X dollars, and with X dollars I can get a sample of N subjects, maybe half treatment, half control. A power calculation, which we're not going to talk about today, but if people are interested later on in the term, I could fit it into a lecture or we could talk about it in section, is a pretty straightforward statistical calculation that tells you, okay, with a sample of this size and with data that has certain characteristics, effectively, what are my standard errors going to look like? And sometimes we do that power calculation and we decide that, in fact, with a sample we could collect, it's actually not worthwhile to do the study because those confidence intervals will be too wide to be informative. So that's the idea with sample. So more sample equals better because of more precise estimates. Yeah?
In randomized experiments, our research targets turns out their randomization process would specifically cut the correlation between the method and other things.
Yeah. Yeah, the way we did it for this paper is this list randomization, which I mentioned was sort of very transparent. We could show it to our partners. This is how we did it. Although ideally you would do it with a random number generator. The kinds of variables you'd be most concerned about being imbalanced with the approach that we used would be some of the variables that were used in sort of stacking the data. For instance, like school population was something that was used to order the schools within each geographic zone. Now, it turns out in our data, those characteristics are actually, like school population, are balanced across the different treatment groups at baseline. But it is a concern. And there's been a lot of debate about how exactly to do a randomization. Some folks, in the past, people don't do this anymore. And we did this for a couple studies. None of them, I don't think, that are on your reading list, but for a couple studies that I did in Kenya and Sierra Leone, we would draw from a computer random number generator 1,000 randomizations or something, or 100 randomizations, and then try to pick the randomization that minimized the difference between the treatment and control group along like 20 characteristics. And you can just come up with some measure that minimizes that difference. Now, these days, people tend not to do randomizations that way. The typical way folks do randomizations now is they specify what those characteristics are that they're interested in, and they do what's called stratification in advance, and then just take one randomization. And there are some statistical reasons why that is slightly preferred, although at the end of the day, I think in practice it doesn't make too much of a difference. So the whole field of development economics has been through this whole evolution of how you actually do the randomization in practice, but the sort of standard practice right now is to say, if I want to make sure I do have balance on a few characteristics, so if you're working on an educational study, you'd probably want to make sure that your treatment and control groups look pretty balanced on educational characteristics. So you would, divide them into groups based on test scores, something like that, and then do the randomization multiple times within each of the different test score subgroups or strata that you're looking at. That way you have equal numbers of treatment and controls with each of these different educational characteristics. Does that make sense? So that's that's the standard practice. And if you're interested in some of the econometrics of this, let me give you a reference for people that want to kind of see how to do this in practice. There's a paper by Miriam Brune and David McKenzie, both of whom are at the World Bank, in the American Economic Journal, Applied Economics, where they basically survey all of the different randomization approaches people have used in their field studies and talk about potential biases in each of them. So, any other questions? Okay. So we went through this last time. If there's no difference in expectation in the unobservable x between the treatment and control group, when we take the difference between the treated and the control, or at least those assigned to treatment and assigned to control, we get B. We get what we want. Okay. So let's turn to the field. This is a picture from the first round of data collection in this sample in 1998. This is a numerator who was working with us, or a surveyor, and a primary school-age girl in Kenya. And you can see the kids lined up behind because surveys were being administered to the kids, to their parents, etc. One thing that we wanted to check, and it gets to this point about balance. You just asked us this question, are you concerned about imbalances? We collected all these baseline survey data to make sure that when we did this randomization, the groups looked similar, that the randomization basically worked in generating comparable groups. So what I'll present here are the averages for group 1, group 2, and group 3 along certain characteristics. Now, in the full paper, we have like 5 times as many characteristics, and we show you that there was balance on a lot of different dimensions. So what did we find? One of the first things we looked at were things related to the home health environment or sanitation environment, having a latrine at home. We already discussed how important latrine coverage is for the spread of worm infections. If you have a latrine and you use it and you're surrounded by others with a latrine and using them, your risk of worm infections are actually much lower. So we want to get a sense here about, in some sense, your access to a latrine tells you something about the risk these kids face in getting worm infections. And there you can see about 81, 82% of the sample actually had a latrine at home. And I mentioned last time that the anthropologists who have studied, the health anthropologists who have studied behaviors around hygiene and sanitation among children in this part of Western Kenya, their findings suggest many young kids might have a latrine at home but don't use it regularly. So I don't think it's the case, it's almost certainly not the case that 80% of these kids were using a latrine regularly. But at least they had one at home. In addition to telling you something about the health environment at home, having access to a latrine also tells you something about an asset, a sort of home infrastructure or investment the household has. So it's probably related to household income as well. So at least on that dimension, the three groups look really balanced, 82%, 81%. I mean, they're very similar. Another aspect of household asset ownership or socioeconomic status we were interested in was livestock ownership. So again, households with lots of livestock would have this wealth that other households wouldn't have, right? If you have lots of cattle, say. So about 2/3 of the sample had livestock at home, and that was totally balanced across the three groups as well. So at least on those dimensions, groups 1, 2, and 3 are looking really similar. It feels like the randomization produced groups that were, observationally quite similar. Now, livestock ownership is a tricky measure of socioeconomic status because among most rural households, it is true that having more livestock means you're better off. But when you get to a certain point in income and you're living in a town and you have a wage job and whatnot, those town folk or city folk may be much less likely to have livestock than people in rural areas, even though they're a lot richer. So, it's not a perfect gauge for socioeconomic status across a whole range of households, but for the bulk of rural households, it is a proxy for wealth. Okay. What are some other important things? This is a health study, a deworming study. So we wanted to know something about child health. We actually asked these questions to parents and kids. This is the answer from kids. Very simple. Are you sick a lot? We also asked them, have you been sick in the last week and what have you been sick with? So there are a lot of detailed questions about what sort of illness they had. But this gives us some sense of kids who are claimed to be sick often. Again, these are quite balanced. 10%, 10%, 8%. There's no statistically significant differences at baseline there. So baseline household characteristics look similar, baseline health looks similar. And then we had a baseline exam score at the school level from 2 years earlier. There had been no 1997 exam that we could get data for. 1997 in Kenya was a national election year. And it was a very turbulent period in the months before the election. And a number of exams, these so-called mock exams that people in primary schools often take at the end of the school year in Kenya, were canceled in that year. But we were able to get the 96 data for the year before. Let me tell you something about how these scores are created. These scores start out on a scale of 0 to 100 or whatever it is, but then they're normalized. And this is the standard approach in the economics of education. So when you see an economics of education study, they don't say, oh, the increase in test scores was from 81% to 83%. That's not how they do it. They normalize them so the mean is 0 and standard deviation is 1 in that population. That's the standard. Now, of course, different populations are going to have different ranges of ability and academic strength. So it's not ideal to always normalize to be mean 0, standard deviation 1, because that standard deviation of 1 could mean very different things in different populations. So imagine the distribution of test scores at Berkeley versus the distribution of test scores across all college students in the US. Across all college students in the US, you get a much wider spread than just being at Berkeley. But that's the norm in the economics of education literature. Typically, an effect size in the economics of education literature, and this is just a rule of thumb, but it's one that floats around, an effect size greater than 0.2 of a standard deviation is typically considered a meaningful effect. Less than that's considered kind of a small effect. That's just the rule of thumb. I don't know why. I just do what I'm told, And so should you. So what do we have here? We have a little bit of bouncing around. There's no statistically significant difference here. We can see group 3 is right on at 0. They're kind of similar to the average for the whole population. Group 2 starts out a little stronger academically. Group 1 starts out a little weaker academically. So it actually turns out the difference between groups 1 and 2 is getting to be kind of meaningful. It's almost 0.2 of a standard deviation, but it's not statistically significant. And what that means is it's sort of the variation you might expect just through natural variation. So overall, the baseline characteristics here, and then in the paper, if you look at the paper, for 20 other baseline characteristics look very balanced. Let me pause for a second. What are some people's thoughts on this table or on the baseline characteristics across the groups? Yeah. It's a very good question. If you don't have that much power, what's called statistical power, in other words, your standard errors are big, then you might have pretty big baseline differences that are not statistically significant, but they could be meaningful. So one of the things that we do, so when we're doing the follow-up data right now, we're doing like 10-year, 12-year, et cetera, follow-up of this sample right now, and I think in a couple lectures I'll mention those results, we control for this variable at baseline. Because this difference is meaningful enough that we feel like we might want to control for it. So that's one approach is to say, look, because of the randomized design, there's no systematic reason why these groups would differ. If by chance we do get groups that differ on some dimension, we could control for that difference at baseline. And that's what folks will sometimes do. Yeah. Yeah, that's the proportion that have any livestock at home. You could. True. One issue there, I think the reason why we stuck with this one in the paper is there's like 5 different types of livestock people could have. They could have goats, they could have cattle, they could have pigs, they could have chicken, and those different livestock have different market values, and it may depend on the age of the animal. And so once you want to put in like a standard measure, like we don't want to say you have 5 goats and 5 cattle, so you have 10 animals, because the cattle are worth a lot more. But then there's different breeds of cows, so we just didn't go like all the way down the road of saying we're going to literally get the valuation of every animal you have to give you a summary measure. So we did this as a starting point. But you could do that. And in some of our subsequent surveys, we have asked for the value of every bit of livestock. Yeah. When we started, we ourselves didn't understand the parasitology that well, so we were concerned about that. It turns out when we spoke to more parasitologists and read the literature, the worm species that the livestock have are different than the worm species that humans have. So even though they have roundworm, they have hookworm, etc., they're different enough species that they can't infect people. The only exception to that is the intestinal helminths that monkeys have are the same as the intestinal helminths that humans have. So monkeys and humans could cross-infect each other. Do you want to grab the mic? Yeah. Sure. Thanks. Okay, thanks. Yeah. Yeah, over 90%, right? So for people who didn't hear, the question is, how is it consistent that only 10% of the kids say they're sick often when we know 90-something% have worms? I think part of it is, some people have light infections where it really wouldn't have too much of an effect on their health. The people with moderate to heavy infections would be more infected. And that's the moderate to heavy people were like over a third of the sample. And this is where we really draw on the medical anthropologists. When they study how people dealt with worms, including kids in this area, worms were just a normal part of life. So it's just like everybody has worms. People see worms in their fecal matter. It's normal. And so that, having worms doesn't mean I'm sick. It's just normal. I have worms. Everybody has worms. So I think it has to do with how people classify health. And if you chronically have worms and you're a bit weaker and lethargic, but that's your normal, then you might not think of that as being sick. So I think people adapt.